Hi everyone, welcome to the lecture series on advanced structural analysis, influence line diagram for a shear at a section in a continuous beam. So let us discuss how to draw ILD for a shear at a section. Take a continuous beam of two span. The first span AB 4 meter, BC 6 meter, and I have a section at D which is 2 meter from support A. Then if I try to draw the beam with a free body diagram, then I have reaction RA, RB and RC. Now because I want a shear at a D, I need to insert a sliding device so that I can remove the shearing resistant at a D. Very important. I'll repeat again. In order to remove the shearing resistance from the D, I need to apply a shear sliding device so that each part of the beam can slide over each other. Then the two sections are separated. Then the sliding device, very important point here, the sliding device maintains the same slope at both sides of the section D. That means slope at D means D1, slope at D2 are same. Then apply a unit load at the D, that is a pair of unit load. Then taking each of the portions separately, AD1 and D2C separately, and first of all I would like to find out the reactions RA for the portion AD1 and RB and RC for portion D2C, taking moment at the respective points. So I will be able to find out the reactions. So let us take portion AD1, which is A, and this is D1, this is RA, and I applied unit load 1 here. Okay, and because there is sliding device shearing distance to be removed, so there will be a movement. There will be movement produced here, which is, let us say, MD. There will be movement produced there. So that also I need to find out. So taking movement at A, I am going towards the left hand side. So LHS clockwise negative. So MD is your anti-clockwise positive. So MD, this 1 into length of this beam is 2 meter. So that will give you clockwise, which is minus 1 into 2 is equal to 0. So MD is your 2 units. Okay. Similarly, now RA must be equal to 1 is straight away. RA equal to 1, which is straight. Because RA plus 1 must be equal to 0. So RA 1 is downward, so minus. So RA is equal to 1 unit. Similarly, taking this portion of the beam, the other portion of the beam, what we can find, taking the right portion of the beam, which is D2, this is D2, and this is B, and this is C. We have RC, RB, and I have a force equal to 1 and applied moment which is equal to 2, and this beam has 2 meter and this is 6 meter. Very important. Now our idea is to find out the reactions RB and RC. So taking moment at C, so what will I get? Moment at C, that means I will be moving towards the right side, that means RHS clockwise positive. So 1 into 8 clockwise, movement also clockwise, and plus RB into 6, which is equal to 0. That means my RB is equal to minus 10 by 6 units. That is equal to minus 5 by 3. So negative. That means RB is downward. So RB plus RC plus 1 equal to 0. That means RB plus RC is minus 1. So subtracting that, so I'll get RC is equal to 2 by 3. Okay. Now, once I found out this, so we can find out the reflection diagram of this structure because of the unit shear applied at the point D. So what happens? If this is my beam, this is A, and this is section D, this is point B, and this is the point C. So what I am doing at this point at D, I am applying a shear. So this section will come down, rotate with respect to A, this goes down like this, and this portion goes up, and this total is unit, and goes down, and goes like this. This is a deformation which is nothing but my ILD. This is ILD. This is ILD diagram. Now it is only matter of finding the ordinate. So if I take a section at X from this, the left hand side portion, that is a distance of X here, this ordinate will be my Y dx. Similarly, if I take a section from this side here, X for this span, for the next span here, this is again X. Okay, so now here ordinate will be my Y dx, and for this span again this will be Y dx. So it's simply a matter of finding the shear force ordinate, which is FD, which is equal to Y dx by Y dd. So total displacement at this portion. Okay, total displacement Y dd. Okay. Now one important condition what I mentioned already, at a D point, slope this side and this side will be same. That means theta dA is equal to theta dC. It's very important. Okay. Second, understanding that how do you get YDD? The YDD is nothing but this YD for the portion D1C. That means YDC y, this will be this alone, I call it as ydc, and this alone I call yda, right? ydc, and this is downward minus, so that yda, but actually this already get negative value, so minus or minus will be plus, so I can say total add up this up. The displacement should be added up because yd already minus. Okay, so simply we take a portion dc and then find out the moment at x section and write the equation of the differential equation, solve for the slope and deflection, use boundary conditions. Similarly, go to the section AD, find the moment at section X from the D, write a moment equation, then different integration, get the slope and deflection, apply boundary conditions, then get the ILD ordinate. Very simple. Okay, now let us look at one section which is the DC, this portion DC. We can also say D2C because we have separated D portion with D1, D2. So if I try to draw this, it is D2, I have a unit force and we have a moment of 2 units. We have RB which is equal to minus 5 by 3 and RC equal to 2 by 3. Okay, 6 meter, 2 meter. So I would like to take a section somewhere here at X. I have another section here. So the mx is equal to, for this portion, and I'm 2 by 3 into x. Now I'm going towards LHS. So while going towards LHS, clockwise is negative. So I'm going to the LHS. So this will produce anti-clockwise, so positive. So 2/3 into x. Then if this is x goes beyond this span here, so again this will produce again anti-clockwise positive. So minus 5 by 3, sorry, RB is minus 5 by 3. Okay, fine. So minus 5 by 3, I should have written downward reaction, but it's okay. So I can write something like this. So this produces the clockwise movement, which is again negative. So minus 5 by 3 into this distance. So this distance will be total your x, and 6 is removed, so x minus 6. Okay. So now mx means ei d square y by dx square is equal to 2/3 x and minus 5 by 3 x minus 6. So integrating one time, what I get? Ei dy by dx is equal to x square by 3 plus c1, the second part is minus 5 by 3 x minus 6 square by 2. Then one more time integrating again, it gives me eiy is equal to x cube by 9 plus c1x plus c2, then minus 5 by 6 x minus 6 whole cube by 3. Then applying boundary conditions, that means at x equal to 0, deflection equal to 0 at C point. So this gives straight away C2 is equal to 0. Then at x equal to 6, that means B support. Again, y 6 meter, y equal to 0, deflection 0 at B support. So that gives me the C1 is equal to minus 4. The same point, right? C1 equal to minus 4. So now writing this C1, C2 into the differential equation. So what I get here, EI y equal to x cube by 9 minus 4x minus 5 by 18 x minus 6 whole cube. This is the displacement equation. Now we also know at x equal to 8 meter. At 8 meter means at a D point, the slope, which is dy by dx, here, if you go to this one, dy by dx, which is nothing but my theta dc, is substituting x is equal to 8, right, and c1 minus 4, what I get, theta dc is your 14 by ei, and we also know theta dc is equal to theta da. Very important. Now the second one, we got a theta dc, theta da. So what is deflection at d? That is your ydc. So ydc is obtained by substituting x equal to 8 meter is equal to. So that means at x equal to 8 meter, ydc, that means take this equation, substitute x is equal to 8. So I get ydc is 1 by ei times 68 by, substitute here. That means 8 cube by 9 minus 4 into 8. Here minus 5 by 8 into 8 minus 6. So adding all, we get a this. This is your 68 by 3 ei. So the deflection from the right hand side. Similarly, we have to get a yda when you take the portion AD. Now let us go to the portion AD. This is A, this is D1. So I have reaction which is 1, and I have movement of 2 units, and this was 1. Length of the portion is 2 meter, right? So everything is obtained. Now I will take a section which is x at distance x in this from D1. So what is the mxx? Now I am going to the LHS. Clockwise is negative, so this is produces clockwise. So minus 1 into x, 2 is anti-clockwise, plus 2. So this is nothing but my minus x plus 2. Integrating, I mean, substituting that mx, which is ei d square y by dx square is equal to minus x plus 2, integrating what I get, ei dy by dx is equal to minus x square by 2 plus 2x plus c. Again integrating one more time, that ei y equal to minus x cube by 6 plus x square by 2 get cancelled plus c1x plus c2. Right, now applying the boundaries, applying boundary conditions, that means at x equal to 0, what is deflection? Or at x equal to 0, what is the slope? dy by dx is nothing but my theta dA. That nothing but my theta dc, which already we got it, which as 14 by ei. Substituting here, theta is equal x is equal to 0. This is your 14 by ei. The c1 is directly 14. Implies c1 is 14. The next boundary, at x equal to 2 meter, that means at a support A, then y deflection will be 0. Substituting into this equation, right? So x is equal to 2 meter minus 8 by 6 plus 4, 14 into 2 plus c1 equal to 0. So I get c2 is equal to minus 92 by 3. So these are the quotients c1, c2, a constant value c1, c2 I have obtained. So now I am looking for deflection at D from the portion AD1. So by substituting in this equation, the YDA is obtained substituting at x equal to 0. That means at x equal to 0, the deflection y is YDA. So from this I get minus 92 by 3ei. Right? Now once I obtain this, so I also want to know what is YDD, which is YDC minus YDA. I told you YDA will always be negative, so minus of minus will be a plus. The total value, the magnitude has to be added up. So which is equal to YDC. YDC we got in the previous slide, YDC here, which is 68 by 3i, 68 by 3ei. This is plus 92 by 3ei. This gives me 160 by 3ei. This is YDD. Now simply it is a matter of taking the ordinate of ILD for each portion and plotting it. So let us see the next. For a portion AD, or it doesn't matter, AD, and for portion AD and DC or CD. For portion CD, the ILD ordinate FD is YDX by YDD, and this has a two ordinates, which is 1 by EI x cube by 9 minus 4x minus 5 by 18 x minus 6 whole cube, the whole divided by YDD is 160 by EA, right? Similarly, for portion AD, FD, the ILD ordinate for shear is YDX by YDD. This is nothing but 1 by EI. YDD for portion AD was minus x cube by 6 plus x square plus 14x minus 92 by 3 whole divided by 160 by 3EI. So this comes out to be, by simplifying this, I get minus x cube by 320 plus 3x square by 160 plus 21x by 80 minus 23 by 40. So by simplifying this FD for portion DC will be x cube by 480 minus 3x by 40 minus of x minus 6 whole cube by 192. So this is the ILD ordinate. By simply substituting for AD portion, x start with the 0 and 1 and 2. Here when start x equal to 0, 1, 2, 3, 4, 5, 6, 7 and 8, we will be able to plot ordinate. So that plot we will be able to get it. So this will be a D portion and goes up, and somewhere here is a B, and let us say this is C, B becomes 0, so this is A and D, B and C. So this ordinate will be 0.575, which is 0.425. So the sum of this ordinate will be 1. This is important. It's very important. Right? The remaining ordinate, let's set 1, x is equal to 1, I get a 0.297. Okay. So at this point the support is there, 0 deflection. At this point support is there, 0 deflection. And at a different 1 meter, 2 meter, 3 meter, 4 meter intervals, I can find out the ordinate. So this is ILD for shear at a D. Thank you.